So hello, everyone. First, I would like to really thank the organizers. This is a really beautiful, great event. I'm very happy to see so many people here in Paris interested in AI and machine learning. So I will talk today about a topic which is generative models and optimal transport. So it's a mashup of two topics, I would say, research topics. So we had a nice introduction earlier by Grégory Renard on GANs. So I will talk about this again. And then I will introduce maybe to some of you this theory of optimal transport. And we're trying hard as mathematicians to make it work for this kind of problem. So first, let me just go back to basic statistics. And so this is really statistics 0.1. And what does a statistician do with reality? What does he do when he sees a bunch of points, such as someone, maybe a company gave him some points and asks him to study those points? Well, he would typically think of, how can I fit those points with a parametric family, a density? So here you can see something that looks vaguely like a Gaussian. And he will try intuitively to make the Gaussian fit his data. So here in this very simple drawing, it's very intuitive. You can see that basically what you would like to see is that the red blob here, which is a contour level set of a density, kind of matches the points. Of course, if we want to play with this mathematically, we need a formula. And the formula was known for many years, and at least we've been using it for a century. And it's called maximum likelihood estimation. So this was an idea that Fisher had in 1912. And basically, mathematically, it amounts to finding the parameter theta, which maximizes the sum of the logarithms of p theta evaluated at each point xi. Okay? So this is really the basics, one of the pillars of modern statistics. So before we move on, I would like to notice with you something which will play an important role, which is that for this formula to work, if some of you here have done math, you know that log of x doesn't exist if x is equal to 0. It blows up to minus infinity. So to make this estimation work, you need that your model, p theta, assigns a positive probability for every point that might come up in nature. Now, let's see what this looks like in practice. Here I just draw you a picture in 2 dimensions. It's very simple. We see what happens. I'm going to draw a picture slightly more complicated in 3 dimensions. I can't go much beyond, of course, because we can't represent things in higher than 3 dimensions. But for the purpose of this talk, just imagine this is a very high-dimensional space. So now, I'm sorry, I jumped a bit to another slide. Another thing that I wanted to say was that there is a geometric interpretation behind maximum likelihood estimation, which is that you're minimizing the Kullback-Leibler divergence of your model to your data. So now let me just go back to what I wanted to say, which was, what happens in practice if you're in 3D? Well, in 3D, you will all agree that this immediately becomes a lot more complicated, right? We start having trouble picturing those level sets of densities. And now we need to fit those densities to those points. In 3D, it sounds okay, but imagine we are in a higher dimensional setting, like very, very high dimensional. And this is what happens with images. So think about an image which is 100 times 100 pixels with 3 color channels, each coded by 256 values, which is very, I mean, all our images are at least this size. Well, this is already a space of dimension 167 billions. So start imagining what would look like just defining a Gaussian distribution on that space. So there's a lot of things that you can do to work around this issue. And for many years, statisticians have, or people in imaging, for this example, thought about finding low-dimensional descriptors of images. But recently, the trend is going the other way around. Basically, rather than put those images in the low-dimensional space and do statistics there, we're trying to go the other way around, which is we will assume that there exists a latent space. So it's a low-dimensional space. And we will look at what happens when you move all those points in the low dimension in this higher dimensional space. And we look at what this surface looks like in this high dimensional space. This is really the intuition behind GANs. So let me give you an example. This low dimensional space maybe might be the vector space of dimension 10. We just take a vector of values, and with that, we create an image. So it might seem a bit counterintuitive to create an image out of something that's so small, but actually there's dedicated algorithms for that. And this is, for instance, the convolution network. So you pipe a small vector on the left, and you get an image on the right. So now look at this picture. What we have here is this manifold, which was generating by this latent space under the action of this f theta. So we call this the push-forward measure of mu under the action of this function f theta. Theta has some parameters. You might think of those parameters as those blocks in the deconvolution network. And now the problem in generative models is to make this surface here fit the data. So we want to change the parameter theta so that we're going to torture a bit this manifold and make sure that it kind of looks like the data. So what can we do to do this? Is there any obvious way to come up with a loss function that is able to tell you how far your manifold is from your cloud of points, the blue cloud of points? Can we do things the old way, as in maximum likelihood, by just plugging in this expression inside our densities? So what I'm just saying is there a way we can replace this maximum likelihood estimation formula by Fisher, but instead of having a p theta here, we just put this f theta push forward mu? And the answer is no. Because obviously, if you look at this manifold, it only covers a very thin portion of the space. It is essentially saying that most of the space has probability 0, and the only area that has a positive probabilities is the very thin space there. So maximum likelihood doesn't work, right? So to estimate generative models, we have to come with a workaround. And one way to do this is to have a more flexible discrepancy function between this manifold and those blue points. So the very nice contribution of the generative adversarial network paper was to come with a very natural, one can say, way to quantify this discrepancy. The intuition was as follows. Imagine that you have your manifold of red points here, your blue points there, and you train a classifier, something that tries to separate the red manifold and the blue points. If a classifier is able to separate properly this manifold and the blue points, it means that they're very far away. So if the accuracy is high, they're far. If, on the contrary, the manifold and the blue points really overlap, as is shown on the picture on the upper left here, then it's going to be very difficult for a classifier usually to come up with a nice way to distinguish the blues and the reds. And so this is the idea of the GANs, which is to minimize as a function of theta what the best accuracy a classifier could get given the red manifold and the blue points. Another trend which has been recently appearing in machine learning conferences in the last year or two is to define or study other types of metrics between probability distributions. So as I said earlier, maximum likelihood is like doing a minimum KL, Kullback-Leibler divergence estimation. Is there any other metric out there? And there's many. If you look back at statistics in the 80s or 90s, you had some very strongly worded papers that were saying, no, you shouldn't do maximum likelihood, you should do this or that kind of metric estimation. So I'm not going to discuss all of those past approaches. I'm going to talk about the one that I'm interested in. So for many reasons that I don't have the time to describe now, I think it's the good one. And it's basically the idea that you can use optimal transport theory to define such a discrepancy between probability distributions. So the one that I will be interested in is the one on the lower right here, this minimum Kantorovich estimation. And if you look at the date, maybe it's very hard, the font is small, but this idea was proposed in the statistic literature in 2006, so about 10 years ago, which is very fresh if you compare it to maximum likelihood, which is 100 years ago. So let me say a few words about this. So what we want to do is to measure the discrepancy between your generative model and the blue points using optimal transport, and more specifically using something called the Wasserstein distance between the two distributions. So in equations, I would like to minimize as a function of theta the Wasserstein distance between the manifold and the data. So where does this word optimal transport come from? So it's not a new field. It's something that's very old, actually. This was started 200 years ago here in Paris by Gaspard Monge, a French mathematician. Maybe if you know the 5th arrondissement, there is a Place Monge, there is a Rue Monge, there is a Monge train station. Well, that's this guy. And then there's been a bunch of, there's a very important Russian economist, a mathematician, Kantorovich, and Koopmans, American Dutch. They got the Nobel Prize for their work on this. And then maybe a more contemporaneous reference is that Cédric Villani's Fields Medal was in part attributed to him for his work on optimal transport theory. So he has 2 huge books on the topic. So if you want to know everything about optimal transport, you can bring, you could bring your Villani book here and maybe get an autograph in a couple of hours. So let me just tell briefly that optimal transport theory is a very dense, very profound mathematical theory. And just recently, we have been able to use it computationally at scale. So we have been playing a bit with it with colleagues. And what it gives us is a geometric toolbox to play with probability distributions. So probability distribution sounds very abstract. But basically, for me, those 3D shapes that you can see here in this picture, for me, they represent probability distributions in the physical space. So there is a uniform mass inside those shapes and 0 mass outside it. And with optimal transport, you can do funny things like interpolating between shapes automatically without any parameterization of shapes. And we've been using this in graphics. And so this is one possible application. We've been also using a lot of these ideas in imaging to do what people call color transfer. So imagine they have a pool of photographs on the left, and you like their color palette. You have one picture in the middle that you would like to recolorize, and then you can try to do it somehow faithfully according to the database on the left. So here, the colors are a bit off, but believe me, this looks a bit better in real. So let me just now start digging a bit more into the concepts, the mathematical concepts. So for the French readers, you will see that what Monge was worried with was transporting basically resources or cement or earth from one location to another. And in French, we call this terrassement. So we have a big pile of earth on the left, and we need to fill up some holes on the right. The volume of the pile on the left is the same as the volume of the pile on the holes on the right. And now he asks, what is the optimal way to do so? If I have a shovel, what should I do to fill up those holes? Should I take the earth on the left side and bring it to the right side? Should I just do things a bit randomly, etc.? And yes, what is the least costly way? And this spanned this whole theory. And so let me just do a bit of math here. The optimal transport, the Monge problem starts from this, the following problem. We have a probability space, a cost function. So this would be probably how costly is it to move some sand from one place to another. And he asked, what is the way that I can know when I pick up some sand at some point x, where I should bring it, t of x? And there is one very important constraint, is that if you just give me this instruction, I really want to make sure that I recover the right pile of sand on the right side, right? So this is the Monge problem. It's surprisingly simple to explain, but actually complicated in mathematics. Some people have made very nice discoveries on this topic for the last 20 or 30 years. This has fueled a lot of the mathematical activity. So let me just quote the result by Brognier about 30 years ago. But if you look at this problem from a data science perspective, it doesn't really work well. For one very simple reason, is that with data, as I showed you earlier, we always play with discrete things. We always play with points. Diracs. We never have access to beautiful continuous distributions. This is why we always try to fit something continuous to something discrete. And so in this case, the Monge problem cannot be solved. Because if you have a lot of sand on one point, you cannot recover, on the other hand, another pile of sand with more structure. So this is why Kantorovich proposed a relaxation of this problem, which was, instead of posing the problem as estimating an optimal map, he said, let's optimate an optimal coupling, so a joint probability distribution. So let me just show you visually what this means. He just said, if I want to compare measure mu on the left and nu on the right, what I will focus on is not maps that bring all the mass from nu to nu, but rather a probability distribution that has the right marginals. This means something like a pile in the middle that can be pushed in one direction to recover the first measure and the other direction to recover the second one. And so he said, among all possible couplings, what is the best, the one that has the lowest cost? And this was discovered simultaneously by Kantorovich and Hitchcock in the 40s. What Kantorovich got the Nobel Prize for was for a dual formulation of this problem. So this problem, we call it a primal optimal transport problem. And Kantorovich came up with a very nice identity that this problem is actually equivalent to another problem where you kind of symmetrize objective function and constraints. Now, to be brief, what I would like to tell you is that this Wasserstein distance is very, very versatile because it allows us to compare points of clouds with points of clouds with continuous measures, or continuous measures with continuous measures. There's no caveat such as the one that you have the Kullback-Leiber divergence. So in terms of scientific production on this topic, well, the upper left part, that is, how can I transport some mass localized in some points to other points? This has been the subject of the whole theory of linear programming since the 50s. So it's a fairly well understood problem, and there are some quick ways to basically improve computation efficiency, and one of them is entropic regularization. The other problems are just starting to be investigated now. So this problem of discrete to continuous is of course very relevant for our GAN or generative model estimation problem. So let me just give you a very quick word on this. So this idea of doing this minimum Kantorovich estimation was up in the air in the late 2006. Then we proposed in an IPS paper in 2016 a case where we could actually do this in a tractable way computationally. Then in 2017 was a very nice boom. There were two nice papers on this subject. One was Wasserstein GANs, that maybe some of you know, and another was Wasserstein ABC. So now you can, there will be, I think, a lot of Wasserstein something papers that will be appearing. Hopefully you can trace this back to this presentation. And the main problem in this setting is how can we differentiate and approximate well this Wasserstein distance, assuming this is really what will solve the problem. And so we've been proposing a few approaches, and I will be just discussing in the last 2 minutes one idea that we've been developing very recently. This is still work in progress. And the main idea comes from an efficient approximation of the Wasserstein distance through regularization. So let me just be brief and tell you that the main idea is that this is Kantorovich dual problem of the optimal transport problem. The Kantorovich problem is a constraint problem. For those of you who know optimization, constraints basically are what make optimization complicated. So one way to solve this complication is to get away with this constraints and regularize things. That is, instead of having something that is okay and then blows up to plus infinity whenever something is not enforced, to pay a price for it. So this is a bit like duality. So one possible and very efficient way to regularize this is to use something called entropic regularization. And entropic regularization is just a slight modification of the optimal transport problem. I don't really have the time to explain all of this to you here, but it considerably speeds up all computations. So I have prepared a few slides here, but I think no human could understand them in less than 30 seconds if you were shown them for the first time. So I'm going to skip them and just tell you that there is a very nice algorithm that we can use to approximate this optimal transport quantity, this Wasserstein distance. And the second thing I would like to say is that this algorithm is not only fast, but this is crucial now. It is what we call in deep learning auto-differentiable. So you have this quantity which is a minimum of something, and then when you have a minimum of something, you have to compute it, and sometimes it's a pain to do it. But here in this case, we have an algorithm which is very simple, and which is just an iteration of very simple operations. And those are the two operations here, and this we call the sinkhorn iterations. So what we came up with is a way to estimate a generative model with this sinkhorn loss, the Wasserstein loss. So if you want more details, you can look at the paper. I just want to conclude by saying that optimal transport is a beautiful theory, very deep, and I believe it can have now a lasting impact in data sciences. I think regularizing it, as very often we see here in machine learning, is a very good trick, is very useful. For those of you who know about the GAN literature, let me tell you that regularization helps you interpolate between Wasserstein and MMD. Again, this regularized information is not differentiable, and there are many open problems. So we will have 2 events at NIPS this year. One will be a NIPS workshop in 2017 in Los Angeles, and again in 2017 in Los Angeles, a tutorial. So we'll be talking a bit longer about these issues. Thank you very much for your attention.